Okay, last class we left off on this problem. We were looking at doing empirical formula data problems, and we had done some previously with, break my iPad real quick. We had done some previously with mass, like we did this one. We did this other one. And we had looked at all of these big rules. So we're starting with masses of each of our elements, and I like to start them with individual lines. So 2 or 3 lines, usually. If we have a percentage, we can convert it directly to grams. The trick is that we're using 100 grams, or pretending like we're using 100 grams of the sample. It doesn't matter how much you use. But the easiest way, just turn the percent into grams, convert the grams of each element into the moles of each element, and then the step that we definitely don't want to forget, divide all of those by the smallest number of moles. We're often not going to have mole ratios, the numbers that we get out from step 3. We're often not going to have numbers from there that are whole numbers. So if we have an ending that's pretty close to one of these endings, then we can multiply by one of these numbers, the corresponding number, to get those numbers, all of the numbers up to whole numbers. And then those numbers are going to be our subscripts for each element. So let's see what that looks like for sulfuryl fluoride. So SF, sulfuryl fluoride, is a fumigant, a gaseous pesticide that's used to treat termite infestations in houses, and it has the mass percent composition as follows. So if you've ever driven around and you've seen that it looks like throwing a clown party at their house, right? It's all tarped and tented up. Sulfuryl fluoride is the key fumigant that they're using in there. There's also a trace amount, like 1%, I think, of chloropicrin, which is a lacrimator. And that's all just fun stuff that's an aside. So each of our elements we're going to convert by the power of magic. We're invoking our 100 grams that we're pretending we have. So we're converting all of these percentages into grams. And then we're going to divide them. So that was our first step. We're going to divide them all by their respective molar masses. And this will convert them into moles. So there's the molar masses, all the grams cancel. We put the numbers into our calculator. Optionally, we use our little ... shortcut to save us from writing all the rest of those numbers. Just don't forget, if you're going to use this ellipsis, the ... you want to make sure that you actually used all the rest of the numbers. We don't have to worry about significant figures in this one particular specific instance, because we're going to round the numbers at the end regardless. All right, we got this far. So this is after step 2. Now we've got moles for each of our things. And what's that important step that I yelled about last class? Yeah, we have to divide them all by the smallest number. So the 0.980, we're going to divide them all by that number. And we get the top one for free because it's a number divided by itself, so that's 1. And this is our cool fact, 1 sulfur for every sulfur. And the other two are about 2. 1.999 ... oxygen per sulfur. So about 2 oxygens for every sulfur. And the other one is a similarly close 1.999. but this is fluorine for every sulfur. These numbers are close enough that we can round. So we're going to round all of them, except for the 1. So we've got a 1 for our sulfur. So S. And then our oxygen, we rounded up to 2. So SO2. And then fluorine, we also rounded up to 2. So we're going to have F2. So SO2, F2 would be our empirical formula for sulfuryl fluoride. Questions or confusions about any of our steps? Cool. We can also calculate percent water in a hydrate. So we've talked about hydrates. I think I mentioned them during our nomenclature chapter, the previous chapter. It was like a little addendum, a little add-on, I think, that I might have done at the end. So many ionic compounds naturally contain water molecules. Lots of ionic compounds, things where there's a metal and a non-metal, these naturally contain water molecules. They naturally want to incorporate water molecules into them. They're called hygroscopic. This is not like a vocab word that you need to know. Hygroscopic just means that they absorb water out of the air. The air part might not be necessary for that, but they absorb water. So an ionic compound, if you just leave it sitting out, a lot of them will just absorb water out of the air because there's water in the air. And when they fill up on those water molecules, we call that a hydrate. Just in this, like in the same way, if you drink a lot of water, you'll be well hydrated. Chemicals can also be hydrated. That water can be removed with heat, and the resulting compound is anhydrous. So this an prefix meaning without or not hydrated. So our key vocab, hydrate. A hydrate is an ionic compound that has water in it. Oftentimes hydrates are colored. They're not always colored, but sometimes they're fun colors like this cobalt 2 chloride hexahydrate. And then we also have anhydrous, which is without water. So some of the chemicals that get used in labs, some of the ones that we use in labs, will absorb water out of the air, and then to get that water out of them, you have to bake them at over 100 degrees Celsius to hopefully get the water out. And we can also calculate percent of water in a hydrate. So for example, Epsom salts are a hydrate of magnesium sulfate, MgSO4. And we've got our magnesium sulfate here. We've got our middle dot that's tagging on or connecting our waters. Remember that this middle dot means associated with. They're just connected together. We're not making any statements at this point about how they're connected. They're just around. So there's 7 water molecules around for every 1 MgSO4. The full name of this would be magnesium sulfate. That's the MgSO4 part. And then hepta is our prefix for 7. And then the hydrate here is referring to our water. We don't do anything to represent the middle dot. We just tag on heptahydrate at the end. What would our full chemical name be for gypsum, this chemical compound? Think about it for a moment, maybe discuss with somebody nearby. We're very quiet talkers today. So our full name is going to be calcium. Calcium is a group 2 metal. It shows up on our periodic table next to the K and then Ca. So it's always going to be a 2+ charge. So we don't have to specify what the charge is. Our oxyanion here is still sulfate. And then for our waters, we've got two of them. So this is going to be dihydrate. So calcium sulfate dihydrate. Just like with mass percent, we can also calculate percent water. So this is the same idea as mass percent. So mass percent was mass of the part. We were looking at individual elements, and then on the bottom was the mass of the whole thing. And then because it's a percent, we multiply by 100%. In this case, the part that we care about is the water, and then the whole thing, of course, is the whole thing. We can pretend like we've got 1 mole of the compound, and then that conveniently turns our molar mass into our mass. These are a little bit more involved because when we're calculating the molar mass, we have to remember to include the 6 waters. So the chemicals that we have in this compound, we've got cobalt, we've got chlorine, we've got hydrogen, we've got oxygen. For our cobalt, we just have one of them, and the molar mass is 58.93 grams per mole for cobalt. For our chlorine, we have 2 chlorines. So we're going to multiply that by the 35.45 grams per mole for chlorine. Here's where a lot of people tend to mess up on these problems. How many hydrogens do we have?
12.
We have 12 hydrogens. So the 6 in front of the H2O multiplies across to both the hydrogen and the oxygen. 6 times 2 means that we've got 12 hydrogens, and the hydrogens are each 1.008 grams per mole. How many oxygens do we have? We have 6 oxygens. So this 6 in front also applies to the oxygen. I've seen people get the number of hydrogens wrong. I've seen people get the number of oxygens wrong. And I've probably seen a whole bunch of other creative ways of forgetting a step. So we want to be diligent when we're doing these. We want to be mindful that there's opportunity for us to make mistakes with these. It's a good idea to go back and check our work. So we're going to put this into our calculator. And for the top part, we're also going to be putting that into our calculator. So this green part, we're calculating for the whole thing. That's going to be the mass of the whole. And for the water part by itself, we're also going to be calculating that, and that's going to be the mass of our part. So I've drawn the 2 different groups to show where we're getting these numbers from. So our whole, the entire thing, 237.92 with units of grams because we're assuming we've got 1 mole, so that's part of our mole unit. And then for the water by itself, 108.09 grams. Part of the formula is we multiply by 100%. So our grams on top cancel with our grams on the bottom. Numbers into calculator. We get 45.0 I think we get at least 4.3. Probably 4.31%. Good news for us, we don't have to calculate the correct number of significant figures for this on an exam. And on the lab, I'll probably just not pay attention to it if we were to do something like this. As long as you don't just write one significant figure. Right, this should go to, we've got 5 on top is what it looks like. We've got 5 on the bottom is what it looks like. There's a world in which we only have 4, potentially. So as long as you've got 4 or 5 here, that's fine. Questions about any of the parts or procedures? Again, it's just an adaptation of our mass percent water, mass percent water. One for us to work on. By us, I mean all of you, and then I'll also do it. Never mind, this is the same exact slide. We love double slides. Okay, another thing that we can do with empirical formulas is we can find the molecular formula. What is the molecular formula? How does that compare to an empirical formula? What's different about the two? Think about it.
Isn't a molecular formula like the smallest multiple of a formula?
It's not necessarily the smallest multiple. It is a multiple of the empirical formula.
It's the unsimplified version. So like the actual formula.
Yeah, it's the actual formula, the actual number of each element. So if you were to zoom in super far and take a picture of what one of the pieces of the molecule looks like, and you counted up the individual parts inside of that molecule, that's the numbers that you would get. So like there's a sugar that's C6H12O6. This would be our molecular formula. Our empirical formula would be a simplified version, CH2O. We can back calculate to our molecular formula. We need an additional piece of information. We need the molar mass to figure out what that whole number ratio is. So if we take our molar mass for the actual formula, and we divide it by the empirical formula molar mass, our simplified formula, that will give us some number n. So like if we took the molar mass of C6H12O6, we divided it by the empirical formula molar mass, the CH2O, we should get 6. Because we're basically counting up what the units would be, or how many multiple sets we would need if we were putting in the molar masses. That's all it is we're figuring out what we divided our molar mass by to get the empirical formula. So to undo this, we would multiply all the subscripts by that number n, in this case 6, to get our molecular formula. And look at that, we have a sugar problem. It's probably the same one that I did. So the empirical formula for fructose, it's a sugar, it ends in ose, is CH2O. Its molar mass is 180.2 grams per mole. So we need the empirical formula molar mass of CH2O. We're going to put the 180.2 grams per mole on the top, and we're going to divide it by whatever CH2O has for its molar mass. At some point, I'm going to stop showing calculations for molar mass. So if you're still feeling a little unsure or a little confused about how to do molar mass calculations, I would recommend stopping by Logan's SI sessions or stopping by the steam room Tuesday, Wednesday, Thursday from 12 to 5 and getting some help from Jonathan or Liz. So this is our molar mass for the empirical formula, our simplified formula, 30.025 grams per mole, and this is going to get us a number. That number is going to be close enough to round up to 6. Or down to 6. I don't remember which one it is. Down to 6. So then we take our CH2O, we multiply, and we get, I don't know why I keep writing 6, C6, H12, O6. We can also pair this with finding the empirical formula first. I don't know if that's what's on this slide. It's not. I was nice. But you can link up the two different types of problems. So I could give you a problem where you get the grams of each individual component, and I also tell you the molar mass of the whole thing. And then what's the total formula at the end? What's the molecular formula, the actual formula? So that's a problem that you could get on an exam. I think I usually give one of those. Okay, one for us to try. Estradiol is an estrogen steroid. It contains carbon, hydrogen, and oxygen. Its empirical formula is C9H12O, and its molar mass is given. Find its molecular formula. I'll give you a couple minutes to work on this, and then we'll finish up the slides. Okay, so we are calculating, hopefully, a molecular formula. Big crack. So we have to find our molar mass for our empirical formula. We need to figure out how many empirical formulas does it take to get this molar mass, this 272.4 grams per mole. That's basically the calculation we're doing. So our formula is molar mass on top. That's the 272.4 grams per mole. And the molar mass of the empirical formula on the bottom. Empirical formula, molar mass. And we'll get some number out. That number is, we had called it N on the previous slides. And that's the number that we multiply each of these subscripts, the 9, the 12, the invisible 1. We multiply all those by that number to get our molecular formula. So the molar mass we were given for our molar mass, the molecular formula 272.4 grams per mole. The number you should have gotten, hopefully something like this, for the empirical formula molar mass, 136.194 grams per mole. That'll give us a number that's right around 2. So we do 2 times our C9H12O, and you should have gotten out C18H24O2. Do we have any specific things along the way that caused us to get lost? We'd like some clarification on. All right, so that'll do it for chapter 4, and now we can start on chapter 5.